Hi, we're going to be looking at the derivative of inverse trig functions today. Throughout the video, I'm going to be asking you to pause the video. At that time, I'm expecting that you take time to figure out an answer as well as compare an answer to someone else's work. I'm also going to hope that you're talking to other people about stuff, so you are not going to be watching this as one fluid video. You will be pausing it at the appropriate times, and you'll also be asked to talk to other people, so make sure you have a partner nearby. The first thing I'm going to ask you to do with your partner is on the screen, and so once I reveal the screen, you can pause the video, and when you're ready, start it up again. There are multiple answers. I'm hoping that one thing you noticed on this graph is the fact that the graph is always decreasing. Doesn't matter where I am, the graph is going down, either sharply or just a little bit. The idea that the inverse cosecant function is always decreasing is going to be important later on. Since we are going to be talking about inverses today, I also want to quickly remind you about inverse functions. Once again, as I'm going through this, you might need to be pausing it so that you can take notes, talk to somebody else, do that at your own pace. I'll go through an algebraic example of inverse functions. Let's just look at y equals x squared. You might remember that one option you had to algebraically find the inverse of something was to literally just switch the x and y in the equation. So x equals y squared, and then solve that for y. So I'm going to take the square root of both sides, which is going to require the plus or minus symbol. And so that's what the inverse would look like, the square root of x and the negative square root of x. If you remember that graphically, that meant that if I graphed x squared, the graph of the inverse would be a reflection over the line y equals x. I would get this graph. It's not a function, I can't call it that anymore. And actually, because it's not a function, I had to graph positive root x as well as negative root x. But if I look at just the graph of y equals x, can you see that the red is being reflected over the green to get the black? And so graphically, what is happening for inverse functions is that one of them is reflected over the line y equals x. We're going to use this knowledge to help us with inverse trig functions and their derivatives. Again, remember that you can pause this as you go through the example, but I'm just going to be talking through it, so pause it as you need to in order to catch up with the notes. We just said that in order to find an inverse function, we could switch x and y. Well, that's still true in trig, except it's more that you're exchanging the angle with y. So write down that equation and see if you have the same thing I do. Remember, when you're exchanging the x and y, you're no longer talking about the inverse sign. We'd be talking about regular sign. So I have 3x equals sine y, which is a function that I could take the derivative of. I'm going to take the derivative of the left and the derivative of the right. And don't forget, y is embedded inside sine, so the chain rule says we would need the derivative of y, which I'm going to write as dy dx. So it might feel like, oh great, I could just go through and divide both sides by cosine of y, and I've solved for dy dx. And actually, we would avoid the fraction here. I'm going to talk about the secant of y is dy dx, but this is not going to be my final answer. It's kind of like the idea of you don't define something with its own word in it. I'm not going to write the answer of dy dx in terms of y if I can avoid that. So I need some replacement for y. And actually, to do that, I'm going to go back up to this right here. And I'm going to take my trig style problem where I'm going to look at it as a right triangle. And what I have here is an angle of y. That's been decided for me, so I'm not going to put theta into my picture. I'm going to put the angle of y into my picture, and that's going to go right here. We know right triangle trig. We also know in this particular problem that the sine of y is 3x over 1. See if you can figure out all three sides to the triangle right now. When you're ready, unpause the video. So if the sine is 3x over 1 and sine is also opposite over hypotenuse, this is what I'm going to have for those pieces. And if I use the Pythagorean theorem on a squared plus b squared equals c squared, I'm going to come up with this is my third side. And the reason that I want that is because of this right here. I would like to know what the secant of y is. So I'm going to write 3, and I'm going to write a fraction for secant. Right triangle trig is going to create a fraction of some kind. And secant, let's see, that's the reciprocal of cosine. Cosine is adjacent over hypotenuse. So now it's going to be hypotenuse over adjacent. Here's the hypotenuse, and here's the adjacent. And there's my answer for what dy dx is. Just a quick reminder here, some of you like to make up math on your own or you forget some things about the different rules. This will not turn into the square root of 1 minus the square root of 9x squared. Those are not equal to each other. So the answer that I have here is truly the answer. All right, let's try another one. How far can you and your partner get through this problem without getting help? Pause the video and see if you can figure out the answer. If you got this far, great. Continue on with my video and see if you got the answer right. If not, fix this and then see if you can correct your mistake. I then drew the triangle that went with the original regular non-derivatized, fake word, function. And now I'm going to have -4 in my numerator. And the cosecant, well, that is the sine as a reciprocal. Sine would be opposite over hypotenuse. So I'm going to put hypotenuse over opposite. So I'm going to say dy dx equals -4 over the square root quantity. Do not try to turn this into, 1 minus 4x squared. Here is my answer. All right, it doesn't seem to go with the warm-up that we had on the calculator. So let's do one more problem and see how the calculator relates to this. Once again, see how far you can get through this problem before you start up the video. Well, here's everything that I have. I don't have the final answer yet, though, so let me go through that piece by piece. So I'm going to take the function that I have here. I'm going to put the -2 in the numerator. And some of you maybe have started seeing that, you know, it's kind of up to you where you want to put your trig functions. Do you want it in the numerator or do you want it in the denominator? Or I guess I just said that backwards. But I personally like having it in the numerator because of the fact that the trig functions are going to cause a fraction. And so now when I look at my sine being opposite over hypotenuse, here's my opposite and here's my hypotenuse. And then when I look at tangent being opposite over adjacent, I can put my pieces into the fraction and they're already in the right spot of the fraction. So it looks like I'm getting a -2 in the numerator, a +2 in the denominator. So it's going to become this, which is x with this square root. So that's what dy dx is equal to. Wait, though, that's not what dy dx is equal to. It's almost what dy dx is equal to, but I want to look back to our original warm-up. If we originally said inverse cosecant is always decreasing, what does the sign of the derivative always have to be? Tell your partner. You should have said negative, which you might think, well, it is negative. That's great. We have a negative right here. That's true, but what if this ends up also being a negative? It's not an issue in the square root. It's going to get squared. So if that x out in front is always a negative, we're going to have an issue. So you need to guarantee that that x in front is positive. And the way we guarantee positive answers in math is to throw an absolute value in there. That is your answer for this question. There's one other trig function where you are going to have to put in an absolute value. Do you have a guess what that is? I hope you said inverse secant. If you see this type of problem and you're looking for the derivative of it, you are going to need to put in an absolute value of x. And basically what ends up happening is if you work through an inverse secant problem, your numerator will naturally end up being positive, and you need to guarantee that the inverse secant's answer is always positive because the graph of inverse secant is always increasing. After doing 3 problems, you might be able to see that there's going to be a consistent pattern between these because we're always going to be drawing a triangle. Depending on the function that you have here, you'll always be using the same sides for inverse cosecant. If the original problem was inverse tangent, you'd always be using the same sides of the triangle. So there are definitely patterns here, and I want you to look at page 185 and check out the rules there. Now before you actually look at page 185, listen to the rest of this. On page 185, there are 24 basic differentiation rules. I want you to figure out which ones have we talked about and which ones did we specifically talk about today. Unpause this when you're ready. The only one that we really have not talked about is rule number 8. That's not one that you need to worry about right now. We've kind of talked about rule 11. It's actually a specific case of number 9. It hasn't come up too much. Today's specific trig derivatives were 19 through 24. And so, yes, you could go through and you can memorize all those. And actually, it's a really good thing to know. You might be able to see, though, with the little the similarities and the little differences that they have, it gets a little confusing. So I really want you to try some using this visual form that we're taking on today. But I also want you to see if you can start just taking a good guess of what the answers are going to be, because it's going to help us when we go backwards to recognize what the answers are when we get to integration. The problems that I want you to try are on our assignment guide. It's day 16, so we've actually skipped over a day. Make sure you're looking at the right problems. And again, try those out with the visual piece of drawing that right triangle, switching them around, etc. But then see if you can start to get to know the basic rules so that you don't have to go through all the work every time. Good luck!